This lecture is on electric vehicles. The transportation sector makes up 27% of U.S. greenhouse gas emissions. This little figure shows us where the greenhouse gas emissions in the U.S. come from 2017 from the EPA. 29% from electricity production and consumption, 27% from transportation, industry 21%, commercial and residential 12%, and agriculture 9%. So in order to deal with climate change and to reduce greenhouse gas emissions, we really need to think about electricity production and transportation. So the agenda today is negative externalities from driving, both gas-powered vehicles and electric vehicles, and then we'll talk a tiny bit about driverless vehicles. So driving is associated with several negative externalities. Recall that a negative externality occurs when one person or company's actions negatively affect others and the others are uncompensated. So these things like pollution are unpriced. Driving gasoline-powered vehicles generates negative externalities such as congestion. If you drive your car, you're kind of congesting the road, and so other people can't drive where you are. We get traffic jams. It reduces, or it causes us not to be able to get places on time or spend extra time in the car. Pollution. So there's CO2, a greenhouse gas that's coming out of your car when you burn gasoline or diesel. There's also local air pollutants. So when we talk about pollutants, we talk about local versus global pollutants. Local pollutants are things like particulate matter, sulfur dioxide, NOx, ozone, volatile organic compounds, things that don't really tend to travel all the way around the world. They go up into the atmosphere and then they might come back down. They may not even go up into the upper atmosphere. That's not to say that they can't. PM 2.5 from wildfire smoke, that travels all over the world. But we generally think of them as local pollutants. The alternative is global pollutants like CO2 or methane, and those enter into the atmosphere and affect the entire globe. So we have both types of pollutants coming from driving gasoline-powered vehicles, and we also have traffic accidents. Those are externalities as well. As a reminder, here are negative externalities in graph form and how they lead to market failure. We have the downward sloping demand curve. Demand equals marginal benefits. We have the upward sloping supply curve, which is the lower of the two parallel lines on this graph, labeled as S, and it's equal to the marginal private cost of the producer. We have an externality, and we've seen how this externality is modeled previously in this class. It's an upward shift in the supply curve. So we have the marginal social cost, which is the upward sloping curve that's higher than the marginal private cost or the supply curve. So that marginal social cost is the private cost plus the externality. And we've labeled deadweight loss on this graph. So if we produce at the intersection of supply and demand, we would be producing at a place where we have deadweight loss. One solution to the externality problem is to tax the activity. And so we've seen this before as well. If we tax at the rate of the externality, on the graph to the right, that's just the tau is the difference between the marginal private cost and the social marginal cost, or the marginal social cost. So it's the difference between those two parallel lines. If we tax at this rate, this is called the optimal Pigouvian tax. It moves the private marginal cost curve so that it matches the marginal social cost curve. So the private, it pushes the marginal private cost curve up to the social marginal cost, and that's S2 in this. It's also going to reduce consumption because we're going to get Q2 on this graph instead of Q1. It eliminates the deadweight loss as well. Are electric vehicles associated with the same externalities? Of course. Congestion, yes. If you drive an electric vehicle, you're going to cause traffic jams just in the same way you would driving a gas-powered vehicle. Pollution, yes, but different. And we're going to look at how pollution differs for electric vehicles relative to gas-powered vehicles in a moment. And traffic accidents, yes, of course, you can still get in an accident with an electric vehicle. In the past, electric vehicle buyers have received a $7,500 tax credit for purchasing an electric vehicle. The question is this tax credit justified, or this subsidy justified? Is it justified in terms of the environmental benefits derived from driving an electric vehicle or replacing a gas-powered vehicle with an electric vehicle? So this credit or subsidy decreases the cost of an electric vehicle for vehicle buyers. It's justified by potential environmental benefits. In the present, how large are these environmental benefits and how do they compare to this subsidy? So we need to ask, how large are the environmental benefits of driving an electric vehicle relative to a gas-powered vehicle? And are those benefits equal to $7,500? If so, then this credit is justified. If not, then we're paying too much in subsidies for in electric vehicles. One thing we might also think about is, are there long-term innovation spillovers increasing the future benefits of driving electric vehicles? So, for example, if you subsidize an electric vehicle, then you are artificially increasing the demand for electric vehicles, which means that car companies are then going to put more energy into research and development on making these vehicles more efficient and also putting in charging stations. So the paper we will look at is Holland, Manser, Muller, and Yates. They investigate the present environmental benefits from electric vehicles. One thing to note is that electric vehicles have no tailpipe emissions. They have no local pollutant, hyperlocal pollutant damages. There's no pollutants coming directly from driving an electric vehicle. But electric vehicles are not pollution free, of course. When you charge your electric vehicle, you plug it in, that electricity has to come from somewhere, and nearly all of the marginal electricity generation from electric vehicle charging comes from coal or gas-powered power plants, gas-fired power plants. And we know that coal and gas are not emissions free, and so there's some emission damages from driving electric vehicles as well. Whether electric vehicles are environmentally friendlier than gas-powered vehicles is an empirical question, and this paper is going to answer that. So Holland et al. Used different models to estimate the effects from 5 primary pollutants of driving electric vehicles and gas-powered vehicles. Human health is the largest source of local pollutant damages, so if we're only thinking about the local pollutants, like, again, particulate matter or ozone or things like that, the largest impact from those pollutants is human health. We might be sending people to the emergency room with asthma attacks if they're exposed to more PM 2.5. We saw a lot of this during the wildfire seasons here last year when the air quality was really bad. People were going to the emergency rooms because they couldn't breathe. So pollution near cities is more damaging than pollution in rural areas because the population density is higher. You're damaging more people's lungs if you're driving in a gas-powered vehicle in a city than if you drive it in a rural area. But greenhouse gases are also very important. Which is more important? It's hard to say. This model or this paper is trying to answer that question. But each of the gas-powered and electric vehicles, they produce some amount of greenhouse gases. And we need to think about which one is producing more greenhouse gases, the gas-powered or electric vehicle. And then we can translate the amount of gases that are produced into damages using a number called the social cost of carbon from the EPA. So this map on the right comes from Holland et al. It shows the marginal emission damages for gasoline vehicles by county in the United States. The marginal damages are the emissions damages from driving 1 additional mile from a gas-powered vehicle. They have a fairly fuel-efficient vehicle as their baseline vehicle, I think it's the Ford Focus. And so what this map shows is there's a lot of green, but red where the population density is highest, like San Francisco, LA, Chicago, New York. So even Atlanta, there's some high marginal emissions damages. And so these are primarily local pollutant damages. You can see most of the United States is fairly green or has low local pollutant damages. But these population centers have really high local pollutant damages because you're exposing more people to more local pollutants in the population centers. So in contrast, this map shows the marginal emissions damages for electric vehicles by county. So again, marginal damages are the emissions damages from driving 1 additional mile, but in this case we're thinking about driving an electric car 1 additional mile. So you'll notice immediately that the difference between the previous map and this map is that this map has these large regions that are all the same color. For example, the western U.S. and the upper Midwest. The western U.S. is all green and the upper Midwest is sort of dark reddish brown. So what this is indicating is that these are interconnected electricity grids. So if you charge your electric vehicle anywhere in the western U.S., California, Nevada, Oregon, Washington, Idaho, etc., the emission or the electricity for charging that electric vehicle is going to come from the same source. The marginal electricity is coming from the same source anywhere in that grid. And that's because electricity can travel at the speed of light around this grid. So you charge your car up in northern Montana, the electricity to charge that car can be produced in Southern California. Same with the Midwest. Why is the Midwest darker than the Western U.S.? Well, that's because most of the electricity being generated in the Midwest is coming from coal power generation. So it's relatively dirty, or relatively more dirty than driving a electric vehicle in the Western U.S. So we've seen in the previous maps that the damages from driving gas-powered vehicles look substantially different from the damages of driving an electric vehicle. So the question is what is the right subsidy for these electric vehicles? We know now that the answer to this question depends on where you're driving each of the vehicles. For the gas-powered vehicles, the question is, are you driving in an urban center and therefore exposing more people to the damages from driving the gas-powered vehicle? For the electric vehicle, the question is, what is the marginal source of electricity generation for charging your your electric vehicle? If you're driving in the western U.S., then it's fairly clean. If you're driving in the Midwest or the Southeast, then it's fairly dirty. And so maybe certainly this answer depends on where you're doing the charging and driving. So what is the benefit of an electric vehicle relative to a gas-powered vehicle? And we've seen this in the previous maps. It depends on where you're driving. And the optimal subsidy should be equal to the present value of the difference in external costs over the lifetime of the vehicle. And so the question is this $7,500 equal to that difference? Is it equal to the present value of the difference in the external costs over the lifetime of the two vehicles? Sort of a side note, is the subsidy efficient? A trick question. No, an efficient policy taxes each vehicle type, gas and electric, and the tax should be equivalent to their external costs. So the subsidy cannot achieve the efficient solution just outright. So we know the subsidy is not the most efficient policy, but if we're going with a subsidy, what's the most appropriate subsidy? The western states have the highest environmental benefits of electric vehicles versus gasoline. We saw this in the maps that the western U.S. had, for the electric vehicle charging, had the cleanest grid. And so the benefits of driving an electric vehicle are highest in the western U.S. relative to anywhere else in the country. So the right this figure shows the environmental benefits per mile for for 5 states in the western U.S. California has an environmental benefit of 1.86. should be cents per mile. Utah is 73.73 cents per mile, Colorado 0.6, etc. The purchase subsidy, therefore, for an electric vehicle in California should be $2,785 according to Holland et al. In Utah, the purchase subsidy should be $1,089. So these subsidies are the present value of the difference in environmental damages from driving the electric vehicle relative to the gas-powered vehicle. So a positive subsidy indicates that the electric vehicle is cleaner than the gas-powered vehicle. In the Midwestern states, where they have the lowest environmental benefits of electric vehicles versus gasoline, they actually find negative subsidies. So you can see in South Dakota, it's much cleaner to drive a gas-powered vehicle than an electric vehicle. We have a negative subsidy, meaning we should, their models suggest we should tax electric vehicles. And that's because South Dakota is relatively rural. You're not really damaging anyone's lungs by driving your gas-powered vehicle there. And charging an electric vehicle in South Dakota is relatively dirty because most of the electricity is coming from coal. The national average subsidy, according to Holland et al., is about negative $1,000 or a $1,000 tax on electric vehicles. So what they're basically saying is that we need to clean up our electricity grid. It also matters when people charge their cars. So people typically charge their cars at night while they're sleeping. The marginal electricity production at night is usually from coal, which is relatively dirty. So if we were able to get people to charge at different times of the day, we might be able to clean up the charging profile. So would electric vehicles look better if charged during the day? Yes, but this is more expensive. The wholesale prices are higher during the day, and we would be increasing the peak load, which would mean we'd have to invest in more generation infrastructure. So just to bring it back to the electricity markets, this is a dispatch curve. With each of the dots representing some amount of capacity being supplied at some price, right? So this is essentially an aggregate supply curve for an ISO. The question is, who's going to be the marginal generator at different times of the day? So in the middle of the night, when demand is low, we might be in the red area, which is coal. So coal has relatively high emissions, and so if you charge your electric vehicle at night, that electricity is coming from a coal generator. But if you charge during the peak hours, if you go out to the right side of this curve, where the peak hours where demand is highest, we would have a vertical line somewhere out to the right, maybe where the furthest right red line is on this graph. The electricity at that time is going to be natural gas, and which is relatively cleaner than coal. So we're doing better by charging during peak hours of the day in terms of emissions. What about long-term benefits? Holland et al. Observed power plant emissions in 2010 to 2012 to estimate the damages from electric vehicles, but since 2012, the composition of electricity generation has changed. We've shifted away from coal toward natural gas, and we've also expanded the renewables on the grid, so the grid is getting much cleaner. And as the grid gets cleaner, then electric vehicles look better and better. If we think of generation will eventually be much cleaner, then maybe there are benefits from starting the transition to electric vehicles now, because if we get to a really clean grid and we already have electric vehicles on the road, then we're a long ways towards reducing our emissions from transportation. So this would be called learning by doing, and innovation spillovers in electric vehicle manufacturing. So the subsidies could be encouraging, as I said earlier, research and development to making the cars more efficient and creating charging stations. There's also what are called network effects, and we'll talk about that now. Electric vehicles have network externalities. A network externality is when the value of a good or service to an individual is greater when many others use the same good or service. So for example, operating systems like Windows, if you were the only person with Windows, you would have a hard time sharing documents with other people. But as more people use it, then there's benefits to this. You're in this network, and it makes it easy. Social networks such as Instagram, search engines like Google, these are all things that benefit from having many other people use them. If more people drive electric vehicles, then firms will build more electric charging stations. It will become more attractive to drive electric vehicles, and so um, if you buy one now, you want other people to buy them so that there's more incentive for firms to create charging stations. Quite simple. These alternative fuels, like electric vehicles, they face a chicken and egg problem, though. We have gasoline available almost anywhere. It takes very little time to fill up your car with gas. Other fuels, electricity, hydrogen are much less widely available, and so consumers are reluctant to purchase cars they may be unable to refuel. With no consumers buying cars that run on alternative fuels, firms are reluctant to make large investments in new fueling infrastructure. We have policy options to deal with this. We have public investment in charging stations. In Colorado, we've taken the money that we've gotten from the Volkswagen settlement, where Volkswagen lied about their diesel emissions. They then had to pay millions of dollars to all states in the U.S. And Colorado has decided to use that money to invest in charging stations. We can keep subsidizing electric vehicles, so that would increase the demand for charging stations, and we could have coordinated electric vehicle charging. So we could get people to charge at different times of the day in order to charge when the emissions are lowest and the price of wholesale electricity is lowest. So one thing I want to note is that this Holland et al. Paper that we've talked about, they show something that might seem a little bit depressing, and they show that the optimal subsidy for electric vehicles in the U.S. is going to be a tax, but this is primarily due to local pollutant damages. I want you to know that electric vehicles, when we're only thinking about greenhouse gas emissions, so things that are affecting the climate, if we're only considering greenhouse gas emissions, electric vehicles are hands down better than gas-powered vehicles. What Holland's paper is really showing is that when we start to think about these local pollutant damages as well, then the gas-powered vehicles start to look better in some cases, and mainly in some parts of the U.S., than electric vehicles. So electric vehicles are not all bad. It's just what you're paying attention to matters. So moving on, we may see driverless cars in the next 5 years. How are driverless cars going to change the transportation market? So car makers are optimistic we'll soon have fully autonomous vehicles, and there's a list here. I know you can't click it through YouTube, but you can pause the video and type this in. But it's a list of car manufacturers considering autonomous vehicles. It requires changes in regulation, infrastructure, insurance, etc. Currently limited federal regulation on this, primarily because we haven't had to think about it yet. We don't have autonomous vehicles. But we do have regulation at the state level. So self-driving car questions sort of the future of transportation. Of the negative externalities associated with vehicles, which is associated with self-driving cars? Congestion. So when we think about self-driving cars, are we thinking about self-driving Ford F-150s or F-350s? Really big gas-guzzling vehicles? No. We're thinking what this is going to look like. It's going to be companies like Uber and Lyft purchasing fleets of small electric vehicles, really tiny, maybe even two-seater electric vehicles that are self-driving. And these companies purchase these fleets and they have them driving around places like New York or really dense population centers. The nice thing about self-driving vehicles is they can be driving very close to one another. So on the freeway, you could see whole trains of self-driving vehicles driving within a foot of each other on the freeway, and they would do this because the first car is sort of braking the air in front of them and making it much more efficient for the cars behind them. Uh, and if you have self-driving vehicles, they can do this because they are talking to each other in real time. So if the front car slams on the brakes, the cars behind it are going to immediately slam on their brakes as well. This is obviously not the case when people are driving cars because people are they don't have reaction times like self-driving cars would, and people are looking at their phones, etc. And so there's some serious benefits to having self-driving cars in terms of congestion. It's going to make traffic much more efficient. What about pollution? Self-driving cars are going to be much smaller, have much less horsepower, so they get much higher fuel efficiency, and so the pollution is going to be dramatically decreased from self-driving cars. We also, again, will see self-driving cars being more efficient on the freeway because they can tailgate each other safely. There will be fewer accidents, hopefully, because self-driving cars don't have lapses in attention, right? You don't have a self-driving car looking at its phone. The self-driving car is paying attention all the time. So as long as we get the algorithms right and the self-driving cars can see people and know when to stop, then we'll have fewer accidents. So are there network externalities? Absolutely. Same as electric vehicles, with self-driving cars, we're definitely going to see network externalities. So this is kind of the future of transportation. And as the electricity grid becomes cleaner and we get more electric vehicles and potentially self-driving electric vehicles, we're going to substantially clean up the emissions and the externalities coming from both electricity and transportation.